Have you ever wanted to go to university but didn't want to learn the disinformation that most universities teach? Well, you can go to Woowoo University, teaching some of the top of the line uh, alternative science options, such as getting stellar atmospheres from Pierre Marie Robitaille, otherwise known as the Sky Scholar, where he will teach you the reality about white dwarfs and other stars and how exoplanets don't exist.
In order to make continued progress for our analysis, let us begin with these spectra from Salmon et al. Obtained for various types of white dwarfs. So far, we have focused on DA white dwarfs such as Sirius B and 40 Iridiani B as represented by the top spectrum. These two stars are the closest white dwarfs to the Earth and have powerful hydrogen-Balmer absorption lines with little or no metallic lines evident. DA white dwarfs are also known to possess quasi-hydrogen molecules and quasi-hydrogen molecular cations in their atmospheres, as we learned in the last video. The presence of quasi-hydrogen molecules and quasi-hydrogen molecular cations can act to strengthen the Balmer lines, and such molecules are very likely to be responsible for any hydrogen-based red shifts. Here is a table that summarizes the key features of different types of white dwarfs. The next type of white dwarf has the classification DB. Such stars can possess spectral lines from neutral helium, whereas in the DO dwarf, helium cation lines are present. In both the DB and DO dwarfs, the hydrogen lines are reduced. DC dwarfs are cool stars with no spectroscopic features, whereas DQ dwarfs are rich in carbon. Here's a quote. Approximately 30 to 50% of white dwarf stars are thought to have atmospheres polluted with metals. The mechanisms by which this pollution occurs are relatively well understood in the case of cool white dwarfs. The diffusion timescales for metals in these cases can be on the order of days. For hydrogen-rich white dwarfs, with effective temperatures, T effective, ranging between 12,000 and 20,000 Kelvin. Therefore, for metals to be observed in the atmosphere, the reservoir of material has to be continually replenished through accretion. However, in the case of hot white dwarfs, temperature effective greater than 20,000 Kelvin, the physics becomes more complex. In this case, the radiative forces in the atmosphere are efficient enough to overcome the gravitational stratification, resulting in metals such as carbon, nitrogen, oxygen, and heavier being present in the photosphere through a process known as radiative levitation. Here is another quote along these lines. Over the past decade or so, the presence of absorption lines from elements heavier than helium in the spectra of single white dwarfs with T effective less than or equal to 25,000 Kelvin has come to be understood, without a doubt, as the result of accretion of disrupted planetismo from their ancient planetary systems. As a result, our knowledge and understanding of the composition of exoplanets have grown significantly through the extraordinary detail and precision afforded by this powerful observational technique. Imagine, now we are going to learn about exoplanets by studying the metallic lines on white dwarfs. Talk about overreaching. Here is another quote. The presence of heavy elements in these objects is now understood as external accretion of matter from a disk of debris resulting from destruction of a rocky object, asteroid, or small planet by the white dwarf's tidal forces. These objects are thus temporarily imprinted with the chemical composition of the polluting body, providing a unique opportunity to study the chemical composition of extrasolar bodies. Wow! Now metal lines on white dwarfs are going to teach us all about the composition of asteroids and small planets, which in all likelihood never even existed. Here is another.
Or you can learn about stellar metamorphosis from Jeffrey Woskowski and how stars become planets over time, and all about their evolutionary tracks.
When people say, oh, well, it's a single evolutionary line. Earth was exactly the size Jupiter was exactly the size Ohlsdorf was exactly the size of the sun. That's sort of missing the point, because
each star has its own unique transformation curve. Think of a transformation curve as the DNA of a star. It is what codes the protein for the star's next stage of metamorphosis. The term hot Jupiter would be a star that is getting ripped apart by a hotter host. That would be a good example of a star that is moving on a faster transformation curve. The term ice giant would be a star that orbits so far away from a host that it has more time to build up an inner core and has more material to work with before the atmosphere is completely lost. So those would be on a slower transformation curve. Transformation curves are not the entire history of the star, but can be used to make a guess of their future and infer their past. Two stars can be on a very similar transformation curve, but have different masses, ages, and a host of other different properties. You could have two stars the same mass, but one be older than the other. As they age, they become more unique, thus will give rise to various characteristics, even though they could all be the same age.
Or you can learn about the sun with Gina Marie Colvin Hill, as she teaches how there are objects coming out of the sun that is not plasma.
There's something strange coming out of the sun, and it's not solar flares. It's big round spheres. Something is not right. There are round spheres coming out of the sun, and this is May the 4th and 5th. And there has been a lot of talk about spheres, like metallic spheres and things like this. This does not appear to be a normal solar eruption at all. And you can even go back. I've only went back 100 frames. Something is here. Something has come through a portal. And it's not just plasma. No, there's some type of round spheres, round objects, a lot of them.